Today I'm going to present my work on the accretion structure of VLERX1 and the cyclotron lines of GX01-2. So to give you a brief outline of the presentation today, for both of my sources I will present the scientific background, the motivation, observations, results, and the conclusions. So X-ray binaries, what are these? These are basically systems in which you have a compact object orbiting around a companion star. Now the compact object can be either a black hole or a neutron star, and we can use the companion star to make a further classification. So for example, if the donor star is less than 1 solar mass, then we classify these systems as low mass X-ray binaries. Whereas if the donor star is more than 10 solar masses, these have high mass loss rates, and we classify these systems as high mass X-ray binaries. Now, given that both of my sources are wind-fed accreting pulsars, the focus of the presentation today will be centered around high mass X-ray binaries consisting of a neutron star. So, high mass X-ray binaries are thought to have large-scale structures. So the first structure I'd like to talk about is the accretion wake. Now, if you look at this figure here, there's a blue circle which represents the companion star. Now, these stars are a lot more massive and more luminous than the sun, and as a consequence, they have vastly higher mass loss rates, meaning that they eject a lot more material from their surface. Now, if the neutron star is in close proximity to the companion star, this means that the compact object can be deeply embedded within the stellar wind. And so as the neutron star orbits around the companion star, you get the formation of a bow shock which decelerates material. And as a result of gravitational focusing, you get dense regions forming or trailing behind the neutron star. And this forms the accretion wake. Now, the next structure I'd like to talk about is the photoionization wake. And this is formed through a different physical mechanism. We have X-rays emitted from the compact object, and those X-rays interact with the surrounding environment, photoionizing the heavy metals within the stellar wind. And what this does is it reduces the efficiency of the stellar wind, where it starts to move slow and forming dense regions, and this is what produces the photoionization wake. So next, X-rays are produced through accretion. And accretion is basically where you have matter falling onto the surface of a compact object as a result of gravity. Now, in this image here, you can see there's a companion star with some stellar wind. Within that stellar wind is the neutron star. So if we zoom in, this is what the neutron star looks like. And we model this as a magnetic dipole on the large scales. And typically, you have the magnetic axis, which is misaligned with the spin axis of the neutron star. And as you can see here, these blue arrows represent infalling matter, which is ionized plasma. And this plasma can couple to the magnetic field lines. And these field lines can they can influence and direct that plasma towards the poles of the neutron star, forming an accretion column. And so if we zoom in here, this is what the accretion column looks like. And if you have matter falling onto the surface of the neutron star at supersonic speeds, then we get the conversion of gravitational potential energy to kinetic energy. And what this does is it heats the plasma, producing seed photons, for example, through blackbody radiation, Bremsstrahlung, and cyclotron emission. Now, these soft seed photons, they can be upscattered through either bulk and thermal Comptonization. And that's basically where you have hot electrons giving energy to the photons, such that the photons can escape the accretion column as X-rays. So this template here is intended to highlight some of the spectral properties of high mass X-ray binaries. So in this example here, the continuum is formed through thermal Comptonization and black body radiation. And you can see in the spectrum that it's affected by absorption or photoelectric absorption, and this suppresses the photon flux as a result of X-rays being absorbed by some material along our line of sight. Also here you can see an emission line, which are typically modeled with Gaussian functions. And then we have here a dip in the spectrum at around 50 keV, which is indicative of a cyclotron resonance scattering feature.